lecture, we are going to look at numeration systems, okay? We're going to look at numeration systems and codes. Now, number systems, as the last time when we met, we tried to understand signals and all that, okay? And then we tried to differentiate between digital and analog signals. The number system basically is frequently used in computers or digital electronic systems. Okay. Now, even though number systems are mostly used within computers or electronic systems, the kind of system or at what stage these number systems will be used would be different from computer to computer. Okay. So, for example, when a user keys some data into the computer, he or she will do it using decimal numbers. That is, if you take the computer keyboard, for instance, and you key in a number, though the number you would key in would be in the form of decimals, the computer itself does not understand that, okay? So it will have to be converted to a different number system that the computer hardware understands, okay? So for example, when a user keys in some data into the computer, he or she will do it using the decimal number. That's the system we all have used for several years for doing basic arithmetic like addition, subtraction, division, multiplication, etc. But like I said earlier, once that information goes into the computer, it needs to be converted into a format that is acceptable by the computer, okay? And this is mostly done using a digital circuitry within the computer. Similarly, when the data is to be displayed after processing on a computer or on a monitor for a user to see, for instance, it will again be in a decimal system, or it will be a decimal number. So again, there you would need that conversion. So conversion from one number systems to another is an important issue to be understood. We would have to understand how to convert various number systems from one to the other and backwards, okay? So there are several number systems, but for the purposes of this course, we are going to look at the decimal number system. We'll look at the binary number system. We would also look at the octal number system and the hexadecimal number system. Now, binary for decimals, you already know that is 0 to 9. And then we have the binary, which is base 2, or decimal being base 10. Then we have the octal, which is base 8. And we have the hexadecimal, which is base 16. Okay. All right. So binary numbers are used extensively in digital electronics and computers. Both hexadecimal, that is base 16, and octal, which is base 8 numbers, are also used to represent groups of what? Binary digits. Okay. Then binary and hexadecimal numbers find wide use in microcomputers. For instance, when you look at these microprocessors, the Arduinos and all that, you would find the usage of binary and hexadecimals a lot in there because of the input and output nature of these, should we say, microprocessors or microcomputers, okay? So that is just an introduction into what we are going to be doing today. Now, let's move on to look at certain things we would want to achieve at the end of this unit. Before we complete the unit, or by the end of the chapter, you as a student should know the decimal, binary, octal, and hexadecimal number systems. You should be able to convert from one decimal or from decimal to binary and from binary to decimal. You should also be able to convert numbers from binary to octal and then from octal to binary. Similarly, you should be able to convert from binary to hexadecimal and hexadecimal to binary. So these are the learning outcomes or the learning objectives of this unit. That is to know or understand what decimal, binary, octal, and hexadecimal number system are, or number systems are, convert decimal to binary, binary to decimal, octal to binary, binary to octal, binary to hexadecimal, and then hexadecimal to binary. So if there are no questions, can we start with decimal number systems? If there are no questions so far, can I start with decimal number systems?
Yes, sir.
All right. So with the decimal number systems, it is composed of 10 numerals or symbols. Now, these symbols are from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the decimal number systems or the numerals involved in the decimal number system. That is, we have 10 symbols as digits, okay? So using the 10 symbols as digits of a number, we can express any quantity, no matter how big or small it could be. You could have 1, you could have 2, you could have 3, 4, 5, 6, 7, 8, 9. You could have 1 and 0 giving you 10. You could have 1, 1 giving you 12. Sorry, 11, 12, 13. So you can have as many combinations to get digits no matter how big they are, okay, or numbers no matter how big they are. So the decimal system is also called the base 10 system because of the 10 digits. Because of the 10 digits, okay? Now, look at this diagram here where you have position value 10 raised to the power positive 3, 10 raised to the power positive 2, 10 raised to the power positive 1, 10 raised to the power 0. Then you have a decimal point. Then after the decimal point, you have 10 raised to the power negative 1, negative 2, and negative 3. This is basically a decimal system consisting of what? Decimal points. Now, when you take any decimal number, okay, the symbol you would find from the far left, or the digit you would find from the far left is what we term as the MSD. That is the most significant digit. And the one you find on the right-hand side is what we term as what? The least significant digit. Since we are looking at decimals, we will talk about digits. But if we look at binary, we will look at it in terms of what? Bits. Okay. So let's take, for instance, the number 3,547.216. Okay. This is equal to the representation here where you have 3 times 10 raised to the power 3. And 10 raised to the power 3 would normally give us what? Can someone tell us? 10 times 10 times 10. What would that be? Anyone?
1,000.
So that would be 1,000. So what this basically means here is that for each and every one of the digits you find in that number, when you take that value, multiply by the base 10 to its position value, plus the same thing done to the next digit, you can get the actual value. Okay. So that is why you see 3 times 10 raised to the power 3 plus 3 times 10 raised to the power 2 plus 4 times 10 raised to the power 1 plus 7 times 10 raised to the power 0. And anything raised to the power 0 is basically what? 1. Plus 2 times 10 raised to the power -1. And that is where the decimal point starts from. Okay. So in general, any decimal number is equal to the sum of what? The products of each digit value and its position value. So kindly take note of that. Okay. Now let's look at the binary number system. Since decimal systems cannot be conveniently implemented in in digital systems, then brings the need to have what? Binary number systems. So the major reason for this is that in an electronic equipment, you cannot represent different voltages and have voltage levels from 0 through 9. Okay. You can only have voltage levels being on or off. You can have a voltage level which is on, middle, half middle, or something like that. No, you cannot get that. So the major reason for this is that it is very difficult to design electronic equipment which can work with 10 different voltage levels. That is each voltage level representing one decimal character. That is 0 through 9. That is very difficult to do. But on the other hand, it is very simple or very easy to design accurate digital electronic circuits which can operate with only 2 voltage levels. Okay. And these voltage levels would be the binary, that is the base 2. So it is because of this reason that almost every digital electronic system uses the binary or the base 2 number system as the basic number system for its operation. So like the decimal system, the binary number system is also a position value system where each bit has its own value or weight expressed as a power of what? 2. So when you look at this, similarly, we have the MSB. Here it becomes MSB because we are looking at binary and then we are looking at bits. So you have the MSB and the LSB. And the position values are to the powers of 2. Okay, so you have 2 to the power 3. If you are taking it from the beginning of the decimal point, you have 0, 1, 2, 3. You have -1, -2, and -3. Okay, So that is how the binary number system is also represented. Now let's look at counting in binary. If you look at this table here, you will see that we have some decimal numbers from 0 to 15. And then when you come to the binary side, since it is to the base 2, and this is a 4-bit binary system that has been represented here. So the LSB, which is the least significant bit, its position value is 0. The next one's position value is 1. The next has a position value of 2. And the next one has a position value of 3. So what happens here is that if we're looking for the equivalent decimal of 0 in a binary system, then if you take 2 raised to the power 0, that would normally give you what? It's normally a 1, okay? 2 raised to the power 1 is 2, and then 2 raised to the power 2 is 4, and 2 raised to the power 3 is 8. So when you look at the first decimal number, which is 0, there is no on anywhere. All the bits are 0. Now when you come to 1, the only bit you would find to be 1 is the bit with the position value 0. That is 2 raised to the power 0. And that is the only point you would have 1. When you look for the decimal number 2 and its corresponding binary, you realize that the position value for 2 raised to the power 1 is what has 1. Anything else is 0. So similarly, that combination is used to represent the binary equivalent of the decimal numbers up to the last decimal number here. Please, are we okay?
Yes, sir.
All right. Now let's look at
Yes, sir.
binary to decimal conversion. So far we have looked at the representation of the numbers in decimal and also in binary. Now, in order to understand the binary to decimal conversion, we normally look at conversion of integer or a whole number and the fractional numbers separately, okay? So we would have two ways of doing this conversion. So we shall look at integer binary to decimal conversion, and then we shall also look at fractional binary to decimal conversion. So let's jump straight into it and then see how we can do this conversion. Now, let's look at, for example, finding the decimal forms of the two binary numbers 111102. Sorry, 11101. Let's take that for example. If we are to convert this into a decimal number, how do you think we would do that conversion? Can anyone help us? Any idea? Any suggestion? So we have looked at this representation here, and we have also looked at the binary number system, and we have compared it with the decimal number system, where we said both of them are position value systems. When you look at how we did the conversion earlier on for this decimal number, using the position value to determine what number we have up here, which is 3547.216. If you are asked to convert this binary digit, that is 1101, which is in base 2, to a decimal form, how will you do it? Can someone help? Someone should give it a try. Yes.
Hello.
Yes. Can you speak louder?
Okay. So, so you write or you use a position value where the
Mhm.
base is t. So you get an expression like this: 1 times 2 exponent. Since the values are 4, the highest exponent will be 3.
Okay.
You will get 1 times 2 exponent 3 plus 1 times 2 exponent 2 plus 0 times 2 exponent 1, then
Mm-hmm.
plus 1 times 2 exponent 0. So the 1 times 2 exponent 3 will give us 8, plus the 1 times 2 exponent 2 will give us 4. Then the 0 times 2 exponent 1 will give us 0. Then 1 times 2 exponent 0 will give us 1. So when you sum it up, you will get 13.
Okay, that is exactly how you go about it. So basically, when you look at the position values of these binary digits, because there are 4 bits, the highest significant bits position value will be what? 3. So when you take the first one, which is the most significant bit, it will be 1 times 2 raised to the power 3 plus 1 times 2 raised to the power 2 times 0, plus 0 times 2 raised to the power 2, which will eventually be 0, plus 1 times 2 raised to the power 0, okay? And then when you sum all these up, that will give you the decimal form. So with this understanding, after this lecture, you can try your hands on, number 1 has been repeated, but don't worry about that. You can try your hands on number 1 again and number 2. Now, with the decimal number representation, where you have a decimal point within the binary, can someone tell us how we would do that one too? Let's take the simplest one, which is the 0.1011. Can someone suggest how we would go about that one as well? Any volunteer? Any volunteer? Okay, so in this case as well, what you would be doing is that after the decimal point, the position value starts from what? -1, right? And then it
Yes.
continues to -2, -3, -4. So in that case, just like we have in this diagram here, if you probably have forgotten so soon, let's reference this diagram again. So after the decimal point, you have 2 raised to the power -1, 2 raised to the power -2, and then 2 raised to the power -3. So similarly, if you are to evaluate this number system or this decimal or binary digit, or this binary number or binary value of 0.1011, then it means that you would first of all have 0 times 2 raised to the power 0, then the decimal point, then you'd have 1 times 2 raised to the power -1. The next one will be -2. The next one will be 2 raised to the power -3. And the last one, which is the least significant bit, would be 2 raised to the power -4. And when you evaluate that, that will give you the decimal form of this binary. So you can try your hands on number 4 as well. Please, are we all clear? Do we all get the understanding?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Then yes. Chris did you want to ask a question?
No, sir. I just said yes to what you said.
Okay. All right. So, with this, we can also look at decimal to binary conversion. Okay. Where we can convert a decimal to a binary. Okay. So, in trying to convert a decimal to a binary system, we usually perform this by using two methods. That is the sum of weights method and then the repeated division by 2 method. Okay. Now, the conversion from decimal to binary is usually performed, like we earlier on said, by a digital computer for ease of interpretation by the person reading the number. On the other hand, when a person enters a decimal number into a digital computer, the number must be converted to binary before it can be operated on. Okay, so let's move on to look at how we can convert from decimal to binary using these two methods. That is the sum of weights method and the repeated division by 2 method. So the sum of weights method for decimal to binary conversion. This method makes use of binary weights. That is, to find a binary number that is equivalent to the decimal number is to determine the set of binary weights whose sum is equal to the decimal number. And this is basically similar to what we did earlier on with the binary digits. So consider, for example, the conversion of decimal number to its binary equivalent using sum of weighted methods. So if we're looking at a number, say 9, it can be expressed as 9 equals to 2 raised to the power 3 plus 2 raised to the power 0, simply because if we are looking at binary equivalent of this, then it means we can have 4 bits, because if we have 1 bit, then it means we're only looking at what? 1. Or we are looking at 0. If we are looking at 2 bits, then it means we are looking at a maximum of what? 2. Sorry, a maximum of 3. And then if we're looking at 3 bits, then we are looking at a maximum of 421, which is 8. And then if we're looking at 4 bits, then we are looking at 8421. That is position values 2 raised to the power 3, 2 raised to the power 2, 2 raised to the power 1, and 2 raised to the power 0. So in this case, in order to get an equivalent binary digit, what would happen here is that this 9 would be represented by 2 raised to the power 3 plus 2 raised to the power 2 plus 2 raised to the power 1 plus 2 raised to the power 0. Now, which of these combinations would give us a total of 9? So when we find those ones, those are the position values that will be 1 in our binary. So let's move on to look at the representation here. So placing ones in the appropriate weight positions, that is 2 raised to the power 3 and 2 raised to the power 0, and zeros in the 2 raised to the power 2 and 2 raised to the power 1 positions, we can write the binary number for decimal 9 as 1001, simply because the least significant bit, which is 2 raised to the power 0, would result into a 1. The next one, which is 2 raised to the power 1, will result into a 2. The next one will result into 4. And the last one will result into 8. Now, for all these 4, which ones can we put together to easily get the decimal number 9? It is 8 and 1. If we put together 8 and 2, that will give us 10. If we put together 8 and 4, that will give us 12. If we put together 4 and 2, that will give us 6. If we even add 1, that will be 7. And that would not give us a decimal number of 9. So once you do it this way, using the positions, the ones that when summed up together would give you that value that corresponds to the decimal number are the ones that will be represented by a 1, and the others will be represented by what? Zeros. Please, do we get it? If you don't want to talk, let me see your thumbs up so
Yes,
that
sir.
I know you are following me. Okay. All right. So let's move on to the second method, which is the repeated division by 2 method for decimal to binary conversion. Hello, Sedem. Go
So
ahead and
please,
ask your question.
I don't understand the one we just went through.
Okay. So here, what we are being asked to do here is to find binary digits that are equivalent to the decimal number 9. Okay. Now, let me take you back a little bit and show you something. Do you remember this table we looked at? Do you recall this table?
Yes, sir.
Okay. So in converting the binary using the position value or using the sum of weighted methods, what it basically means here is that, let me see if I can write for you to see. My stylus is not here, but let me do my best to see what I can do for you. So when you look at this bits of binary, you would see that, just 1 second. You will see that when you take this, for instance, which is 2 raised to the power 0, that is the position value of that binary digit. So 2 raised to the power 0 would normally give us equals to what? 1. 2 raised to the power 1, it's basically equals to what? 2. And then 2 raised to the power 2 means that 2 times 2. And that will be
2
equals to
times
what?
2,
Equals to 4.
4.
And then 2 raised to the power 3, it's basically 2 times 2 times 2. So 2 times 2 is 4 times another 2. That will give us what? 8. Okay. Now, if we are to move on to try and use the sum of weighted methods for finding the value of the decimal number 9, what will happen is that because we have the number to be 9, and we know that in binary, if we have 1, 2, the position values in their weighted sums, 2 raised to the power 0, which is 1. So it means we would have 1, we would have 2, we would have 4, and we also have 8. Now, which of them or which of these combinations would give us the decimal number 9? It is 8 and 1.
1.
So what happens is that our 8 is represented by a binary 1, our 1 is also represented by a binary 1, and the remaining digits or the remaining bits are zeros, because when we put them together, we won't get that number. Let's take, for instance, 12. Let's try and convert 12 into a binary. What it means is that similarly, we have 8, 4, 2, 1. Which of these combinations can easily give you 12? If you take 8 and
8
1,
and
you
4.
would get
8
9.
and 4.
Exactly. So it means it is these two combinations. So we'll get 1, 1, 0, 0. Sadam, do you understand now?
Yes, sir.
Okay, let's move on. All right, now let's look at the conversion using repeated or repeated division by 2 method for decimal to binary conversion. Now, here it is a systematic way of converting integer numbers from decimal to binary. And this would normally follow a certain step. And the step for conversion is the first step. Begin by dividing the given decimal number by 2. Then step 2, you divide each resulting quotient also by 2 until there is a 0 whole number quotient. Now, step 3, the remainders generated by each division from the binary number is what you would use to represent the binary equivalent of that decimal. So we will look at an example so that you can appreciate what we are talking about. Now, the first remainder to be produced as usual will be your least significant bit. That will be the first one at the top. And then the last one would be your most significant bit. Sedem, do you still have a question, or it's the first hand that you raised?
So I think it's the first hand I raised.
Okay, I'm lowering it, but you can also do it anytime. All right. Okay, so let's take an example and see how we can do that conversion. So, let's take, for instance, the decimal number 10 and see how we can convert it to a binary using the repeated division by 2. We could have done this easily by using the sum of weight method. But since we have been instructed to use the repeated division by 2 method, we will do that example for you to see. So here, what is happening here basically is that this 10 is divided by 2. And after the division, we get a value 5 with no remainder. So since there is no remainder, we'll represent the binary as what? 0. That will be our least significant bit. That will be the bit on the right hand side. Then the next one would be taking this quotient, which is 5, and dividing it again by 2. And when you divide 5 by 2, you would get what? 2 with a remainder. Now, since there is a remainder, we would represent that remainder with what? A 1. Take the 2, divide it by 2 again, and there will be no remainder. So since there is no remainder, we would get what? 0 again. And remember, in the rule, it says that you divide until you get a 0 whole quotient number. So 1 divided by 2 would give us what? 0.5. And that, we only pick the 0. And that has a remainder. So we would take what? 1 for that. And so it means that the binary equivalent of 10, starting from the most significant bit, which is the bottom, would be 1010. Please, do we all understand?
Yes, sir.
All right. So with this understanding, you can try your hands on the examples given here. That is, try to convert 19, 45, 28, 35, and 15 when you are going over your lecture notes, okay? Now, let's look at
Okay, sir.
the octal number system. The octal number system. Now, the octal number system provides a convenient way to express binary numbers and codes. This system is composed of 8 digits. Since we are talking about octal, we will start from 0, 1, 2, 3, 4, 5, 6, and end at what? 7. That is the octal number system. So to count beyond 7, we form 2-digit combinations in the same way as discussed for decimal and binary numbers. So in this case, when you have an octal number where you see 1, 0, it doesn't mean decimal 10. It means something different. So normally you count from 0 to 7, and then if you need 2-digit combinations, the next one will be what? 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And then when you get to 1, 7 again, you would move on to 2, 0, 2, 1, and so on. And similarly, they also have what? Position weights or position values. Okay. So you see the representation there as well. Now, let's look at octal to decimal conversion. Octal to decimal conversion. The octal to decimal conversion is a useful tool in the field of digital electronics or computers. Now, since the octal number system has a base of 8, each successive digit has a position weight of 8 raised to the power 0. The next higher digit has a position of 8 raised to the power 1. The next one 8 raised to the power 2, and so on, like we looked at for the other number systems. And then in an instance where you have a fraction or where you have a decimal point, you would also have 8 raised to the power -1, -2, and so on. So kindly take note of that. Now, if we need to convert an octal number to a decimal number, there are some steps we need to follow. The first thing we have to do is to write the octal number. And then directly under the octal number, we write the position weight of each digit working from the right to the left. That is working from the least significant bit, or sorry, least significant digit. Yes, the least significant digit to the most significant what? Digit. I keep changing the binary and then the digits. Then you multiply each octal digit by its position weight and take the sum of the products, just as we did for the binary. Okay, so let's look at an example here. So let's take, for instance, in order to illustrate the method, consider an example of converting 2000 or 2374 to the base 8 to base 10. So what you do here for step 1 is that you write the octal numbers down, or the digits within the octal number, as was stated in the rule or the step. Then the next thing you do is to write the position values underneath. So if we're moving from the least significant bit to the most significant bit, this is our least significant bit. Okay. So this being our least significant bit, and this being our most significant bit, we will start off from 8 raised to the power 0, 8 raised to the power 1, 8 raised to the power 2, and then 8 raised to the power 3. And then when we are done with that, we come to the next step. And in the next step, we will take the value or the digit and multiply it by the position value, the weight of the position value. That will be 2 times 8 raised to the power 3 plus 3 times 8 raised to the power 2 plus 7 times 8 raised to the power 1 plus 4 times 8 raised to the power 0. Now, when we evaluate all these, we would get the first one giving us 2 times 5, 1, 2. The next one giving us 3 times 64, 7 times 8, and then 4 times 1. And when we sum all these, that would now become what? Our decimal number, like we have here. Please, do we all understand?
Yes, sir.
Yes, sir.
All right.
So, sir.
Now, let's look at decimal to octal conversion. How do we convert a decimal number to octal? We have looked at the conversion from octal to decimal. So we have integer decimal to octal conversion. In order to convert an integer decimal number to its equivalent octal number, we use a repeated division by 8 method. So here we are using a repeated division by what? 8 method. And the first step is we begin by dividing the given decimal number by 8. And then whatever the resulting quotient is, we divide that as well by 8 until there is a 0 whole number quotient. Okay? Did I repeat this slide? Okay. And similarly, the remainders are generated by each division from the octal number. The first remainder to be produced is the least significant digit, that is the LSD, in the octal number. And the last remainder to be produced is the most significant digit, that is the MSB. In other words, reading the remainders from bottom to top constitutes what? The octal number. So let's take an example here. Let us illustrate the procedure by considering the conversion of 359 or 359 to its decimal equivalent. Sorry, this should be from decimal to octal. So it should rather read octal equivalent. I'll try and do that correction on the slide and share it with you again. So when you take 359 divided by 8, you would get 44.875. Now we take the 0.875 and multiply it by 8. So if you have your calculators with you, kindly do this maths and let's see what you get. So
Yes,
0.875 times 8 gives us what? 7.
7.
And that becomes what? Your least significant digit. Then the next thing you do is that you take the 44 and you divide it by 8 again. And you get 5.5. So you take the 0.5, multiply it by 8, and that gives you 4. Then the next one is taking the 5, dividing it by 8, and that gives you 0 point something. So at this point, you only pick the 0.625 and multiply it by 8. And whatever value you get becomes what? Your most significant digit. So you stop when the whole number quotient is what? 0. Please, is this clear?
Yes, sir.
All right. Let's then move on to look at octal to binary conversion. Octal to binary conversion. Now, the primary advantage of the octal number system is the case with which conversion can be made between binary and octals. The conversion from octal to binary is performed by converting each octal digit to its 3-bit binary equivalent. Now, the table below, or the table you see here, shows the 3-bit binary equivalent of the octal digit. What is happening here basically is that, like we said earlier on, if it is 3 bits, then it means that we have two, 1 second. If it is 3 bits, then it means that we have 2 raised to the power 0. We have 2 raised to the power 2. Sorry, 2 raised to the power 1. And then we have what? 2 raised to the power 2. So this, if we have any value that we want to check, if it is 1, it means that 2 raised to the power 0, which is 1, and then the remaining will be what? 0, 0. If we're looking at 4, for instance, 2 raised to the power 2, which is 4, would now become 1, and the rest will become what? 0, 0. Okay? But there are instances where you can have a lot of binary digits. So let's look at an example with a conversion from octal to binary. Now, referencing from that table, let's take, for example, the conversion of 13 to its equivalent binary from octal. What we said is that we pick each digit and find its corresponding what? 3-bit binary representation. So in this case, or for this representation here, you will see that 3 here would normally have a representation of the position here is 1. The position here is what? 2. So when you take it in that form, you would normally have what? 1, 1, 0 representing the 3, and then the first one, which is what? 1, 0, 0 representing what? 1. So at the end of the day, 13 to base 8 is simply 001, 011. And since there are 2 zeros, or there are zeros preceding the 1, we can knock the 0 off and write 1001. Please, do you understand?
Yes.
Yes, sir.
Okay. All right. Let's make progress then. Similarly, we can also convert from binary to octal. And in converting from binary to octal is the reverse of what? The octal to binary conversion. So we followed this procedure for converting the binary number to its octal value. So for instance, having 100111010, since we want to convert it to an octal, what we'll do is that we'll group them into 3 bits each. So you realize that the first 100 is grouped here. The next, which is this one, is also grouped here. And then this next set of 3 bits is also grouped here. So at the end of the day, knowing how to convert binary to any numeral, we just know that this is 2, this is 7, and this is what? 4. So we have 472 to the base 8. And that is how to convert from binary to octal. Please, any question?
Sir, please, can you go back table? I just want to take a screenshot.
You want me to go over what?
No, not to go over. Please go back to the 3-bit table.
Oh, okay.
Before you started, yeah. I just want
This
to take a
one?
screenshot. Yes.
Is it this one you're asking?
Okay.
Hmm.
Yes,
In
sir.
fact,
It's okay.
after the class, I will share the recording with you so you can watch it anytime you want, okay?
Okay, sir.
Hmm.
Okay, sir.
So what we just did is what has been illustrated here. So there are some examples for you to try your hands on, okay? So you have convert the number 101,110,01 to octal, okay? Now, what happens here is that when you take this, for instance, when you take the first 3 bits and you take the next 3 bits, here you'll be left with only 2 bits. So what you do is that you add 0 to it and you should be fine, as has been demonstrated here. So anytime you take the 3 bits, if you have less than 3 bits, just add zeros to that one so that you can use it to evaluate the equivalent octal value for that. Okay, so you can try your hands on these examples as well at your leisure time. And then we move on to the hexadecimal number system. Now, the hexadecimal number system, like the octal number system, is used mostly as a shorthand, okay, as a shorthand way of displaying binary numbers because it is very easy to convert between binary and hexadecimal. As you are aware, long binary numbers are difficult to read and write because it is easy to drop or transpose a bit. Assuming I'm writing a binary number, let's say 0, just 1 second. Let's say I am writing a binary number 0. 1, 0, 1. Plenty of them, assuming I'm writing about 10 of them. When I write it and you have to even read it, the possibility that you may read a 0 to be a 1 is very high. So very often in displaying, we normally use the hexadecimal to display the binaries in some cases. And then in some cases, they use the 7-segment display. That is where you see this LED displays on the streets where it can represent both binary and what? Alphabets or decimals as well. Okay. Since computers and microprocessors understand only ones and zeros, it is necessary to use these digits when you program in machine language. Have you guys done any programming language so far? Hello?
No, sir.
Okay, so normally when it comes to programming or programming languages are divided into sections or into categories. We have low-level languages, we have mid-level languages, and then we have high-level languages. Now, the low-level languages are the languages the computer hardware can easily understand. And most of the time, we call those ones the machine or the assembly languages. Now, these machine languages are represented basically with what? Zeros and ones. And that is the language any computer hardware understands. Okay. So when there is the design of any computer system, it is very necessary to use these because of the language that the computer hardware easily understands and can easily work on. Okay. Now, the hexadecimal number system is composed of 16 digits, which includes numerals and alphabets or alphabetic characters. Now, these 16 digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The next digit, which will be the 11th digit, is represented by an alphabetic character A. The next one is B, C, D, E, and F. So most digital systems process binary data in groups that are multiples of what? 4 bits, making the hexadecimal number very convenient because each hexadecimal digit represents a 4-bit binary number. We would get to understand what I am saying further in a short while. So let's look at this table here. We have looked at the decimal. We have looked at the binary. Now we want to also look at the hexadecimal. Now, just 1 second. Let me use the highlighter so that I can easily explain certain things to you. So here we have the decimal in this whole area. And then we have the binary equivalent of these decimals. And we have their hexadecimal equivalent. So the binary equivalent of decimal 0 is what? 000. We are looking at hexadecimal, so we are looking at 4 bits now. So the binary equivalent is represented by 4 bits. So we have 00000. Then the hexadecimal is also 0. That representation, which you already understand, let's continue from 9. You will see that the binary equivalent for 9 is what? 1001. It is the same thing, 9 for hexadecimal. But when we get to 10, where you have a decimal representation of 10 or 10, its binary equivalent is 1010. That is 8 plus 0 plus 2 plus 0. That is 10. But in this case, for hexadecimal, it is equals to what? A. So that is where the alphabetic character begins. So you get to the 16th value. So 11 is B, 12 is C, 13 is D, 14 is E, and then 15 is what? F. Since it is hexadecimal, we are looking at 16 values, but those 16 values start from what? 0 to 15. Please, are we clear on this table?
Yes, sir.
Yes, sir.
All right. So if we are clear, let's proceed. Now we look at the procedure to convert a hexadecimal to a decimal number. Okay. How to convert a hexadecimal to a decimal number. Now here, what happens here is that you write the hexadecimal number, then directly under the hexadecimal number, you write the position weight of each digit, working from right to left. And then you multiply the decimal values of each hexadecimal digit by its position and take the sum of the products, like we did for binary and decimal. So in this case, let's look at an example. So in this example, we are to convert E5 to its equivalent decimal number. So this is a hexadecimal representation of a value. We want to understand what this value is in a decimal form. So the first step, we write E and 5, and then using the position values and the position weights, we have 16 raised to the power 0, and we also have 16 raised to the power 1. So E times 16 raised to the power 1 plus 5 times 16 raised to the power 0. And from the table, you know that E represents what? 14. So 14 times 16 plus 5 times 1, which is 224 plus 5, which gives us 229. And that is our decimal value for the hexadecimal value E5. So there is a try question there, which you can try your hands on. Convert the hexadecimal number 2A616 to its equivalent decimal number. Yes. Someone wanted to say something. Yes, Japheth.
Sir, we are converting to decimal, so why not base 10? and rather 16 exponent
We
0.
are converting from base 16 to base 10. If you remember, when we were converting from octal to base 10, the position value we use is 8 raised to the power. When we are converting from decimal to from binary to decimal, we use 2 raised to the power. Javed, do you remember?
Yes, sir.
Okay, so that is the reason why. It is because we are moving it from the base 16. That is why we multiply by 16, so that we can get its actual position value and weight.
Sir.
All right. And I think, Sedem, you wanted to ask a question. I don't know if it was a comment you passed or it was a question you wanted to ask. Just for clarification, confirm what it was.
No, no, sir. I didn't want to ask a question.
Okay. All right. So
Yes, sir.
that is basically what it is for the hexadecimal to decimal conversion. So you can try your hands on that example in the slide. Okay. All right. Let's make progress. I think my spelling of decimal here, I didn't look at it very well. Let me just correct it before we move on. Um, Give me 1 second. Oh, what did I just do? So decimal, I think the same thing happens here. Okay, now let's look at conversion from decimal to hexadecimal. So here the procedure is that we begin by dividing the given decimal by 16. So it's similar, we do repeated division, but in this case, instead of repeated division by 2 or repeated division by 8 or multiplication, we would do repeated division by 16. So the first divide or begin by dividing the given decimal number by 16. Divide each resulting quotient by 16 until there is a 0 whole number quotient. The remainders generated by each division form the hexadecimal number. The first remainder to be produced is the least significant digit, and the hexadecimal number, and the last remainder to be produced is the most significant digit. Note that any remainder that is or are greater than 9 are represented by the letters A through F. So you take note of that. So let's look at an example here and how that conversion is also done. So let us illustrate the procedure for conversion of the decimal number 650 to its equivalent hexadecimal number. So the first step, 650 divided by 16 gives us 40.64. Okay? And we have 40 with a remainder of what? 0.625. When we multiply the 0.625 by 16, what do we get? Can someone try with their calculator?
10.
So, and then in the hexadecimal table, we know that 10 stands for what? What is the representation of 10?
A.
A.
A. So in that case, we have what? We have A. Then the second one, you take the 40 itself and you divide by 16. And then you get 2.5. So you take the 0.5 and multiply it by what? 16, and that gives us 8. Then we take the 2 and divide it by 16, and that gives us 0.125. When we multiply the 125 by 16, we get what? 2. And so our hexadecimal equivalent of 650 becomes 28A or 28A. Please, is it clear?
Yes, sir.
Is it clear or not?
It's clear.
Okay. If it is clear, then let's also look at how to convert from hexadecimal to binary. From hexadecimal to binary. Okay. So, like the octal number system, the hexadecimal number system is used mostly as a shorthand method for representing binary numbers. Okay. So for conversion, each hexadecimal digit is converted to its 4-bit binary equivalent. And the procedure for doing that conversion is as follows. You first of all write the hexadecimal number. Then you write the 4-bit binary equivalent for each hexadecimal digit. Then check if there are any zeros on the leftmost position of the binary number obtained. If there are, you drop off the zeros and write the answer as your binary number. So let's look at an example here. So consider